All right, so in this video, I'm going to go over the calculus of hyperbolic functions. Hopefully, by the end of this video, you will know the derivatives and, of course, the related integrals, which are just the reverse of the hyperbolic and inverse hyperbolic functions. I'm not going to go over how to take the derivative of all of these. Number one, mostly because they follow very similar rules to regular trig functions. The only thing you have to watch out for is when the sign changes. Other than that, it's just pretty much doing regular trig functions. The other thing I want to make sure I mention to you is if you want me to do the other functions, if you want me to show you the proofs for the others, I will happily do that. I can do it in another video or I can do it in class. You just have to let me know. But I'm going to start off with hyperbolic sine. Now, the first thing I did was I rewrote it in its definition form. So I wrote e to the x minus e to the negative x over 2. Since I'm dividing by a constant, I can take that constant out, which is 1/2, and we'll multiply by the derivative of e to the x minus e to the negative x. My next step is to split up using the difference rule, which is just say take the derivative of e to the x and then subtract the derivative of e to the negative x. That being said, I can take the derivative of e to the x. It's just e to the x. And I have to apply the chain rule with e to the negative x. I'm going to have e to the negative x times the derivative of negative x, which is -1. Those double negatives will cancel, so I'll have e to the x plus e to the negative x, and I'll rewrite that as a fraction. We'll write it as e to the x plus e to the negative x over 2. Now, that's the definition of hyperbolic cosine. So notice again, like I said, the formula pretty much stays the same. The derivative stays the same for hyperbolic functions as with trigonometric functions, because if I took the derivative of sine, we would get cosine. If I take the derivative of hyperbolic sine, I get hyperbolic cosine. So let's try doing another one. Let's do tangent. Now, it's important to notice again, I'm going to end up following the same kind of formula, but I'm going to have to use the quotient rule in this case. So let me go ahead and start off by writing this down. So we're going to have um, the derivative of the numerator times the denominator, which is e to the x plus e to the negative x, minus the derivative of the denominator times the numerator, which is e to the x minus e to the negative x, over the denominator squared. So e to the x plus e to the negative x squared. So some things that I'm going to look to try to do here is I need to take the derivative of the numerator, which again, e to the x is going to stay the same, so it's just going to be e to the x. I'm going to apply the chain rule with that negative e to the negative x, and good thing for us, that just turns into positive e to the negative x. But I also need to take the derivative of the denominator. So if I take the derivative of that denominator there, which is e to the x, we get e to the x. And I'm going to apply the chain rule to that e to the negative x. So I'm going to get minus e to the negative x. Now, it's going to be a little interesting here in this case because I've got some kind of special functions up here in the numerator. So what I'm going to go ahead and do is I'm going to go ahead and multiply this out and hope that some of these things kind of cancel themselves. So that's going to be kind of important. So let's go ahead and do e to the x times e to the x, which is going to give me e to the 2x. E to the x times e to the negative x, that's going to give me e to the 0, which is just 1. Then we'll do another one of those, so we'll have plus another 1, and then we'll have e to the x times e to the negative x, so we'll have plus e to the negative 2x as my part of the numerator. Then we're going to subtract, and we will have e to the x times e to the x, which is going to be e to the 2x. We're going to have e to the x times e to the negative x, so that's just going to be plus 1. Then we're going to have another one. Oops, excuse me, that's a minus 1. My apologies. Not a plus 1, because we have a negative and a positive, so that's minus 1. We're going to have another one, because negative e to the negative x times e to the x is going to give me -1. And then we'll do e to the negative x times e to the negative x. That'll be plus, since they're both negative, e to the negative 2x. I am going to go ahead and try to cancel some of the stuff out. E to the 2x minus e to the 2x, e to the negative 2x minus e to the negative 2x. But don't forget to distribute this negative, so we'll end up 1 plus 1 plus 1 plus 1, which is 4 over e to the x plus e to the negative x squared. I'm going to split that up just for a moment just to prove my point, which is e to the x plus e to the negative x, excuse me, under 2 times 2 over e to the x plus e to the negative x. Again, this is just the reciprocal of cosine, so this is secant hyperbolic times secant hyperbolic, which is secant hyperbolic squared. So like I said, it's going to follow essentially the same formula. It's going to do the same thing. The only real difference that we got to watch out for is a sign. And this last question will prove my point. So in this last one, we have secant, hyperbolic secant, which again, I wrote as the definition, 2 over e to the x plus e to the negative x. I am going to rewrite that since there is no real numerator. I'm just going to write it as 2 times e to the x plus e to the negative x to the negative 1. So instead of having to apply the quotient rule on this one, I'm just going to apply the power rule. So I'm still going to have that 2 out front. So I'm going to leave the 2. And so what I'm going to multiply is that negative 1, that my power, times e to the x plus e to the negative x to the negative second. And then I have to perform the chain rule on this e to the x plus e to the negative x, which is going to give me, I'm going to write it down below, e to the x minus e to the negative x. So I'm going to have to multiply all this kind of stuff together. So let me just kind of move this stuff around a little bit then. So I'm going to move the negative 1 out front because that's going to kind of be important in a minute. I'm still going to have the 2, and I'm going to go ahead and put it over one of those e to the x plus e to the negative x's. Notice there's 2 of them because it says it's squared. And then I'll go ahead and write this e to the x minus e to the negative x on top, e to the x minus e to the negative x over the other e to the x plus e to the negative x. So again, I've got 2 of them. There's the first one, there's the second one. So again, that's really important there. So I've got all of the terms. I just had to rearrange them a little bit. Now, this 2 over e to the x plus e to the negative x is, in fact, my secant function, the hyperbolic secant. And this e to the x minus e to the negative x divided by e to the x plus e to the negative x is, in fact, my hyperbolic tangent function. The only real thing that I have to remember is that that's going to be a negative. Okay, so the question becomes, is there really a pattern to trying to figure this out? And the answer is absolutely yes. And so the thing to remember here, and I want you to pick up on this pattern, is notice sinh didn't have a sign change. Tanh didn't have a sign change, but sech did. Now the question is why? Well, the reason is sech is a reciprocal function. So that means if I have sech, which is secant, hyperbolic secant, or if I have cosec, which is hyperbolic cosecant, or if I have cotangent, hyperbolic cotangent, that's going to be a negative. However, the cosine isn't going to change signs like it did before. So that's an important thing to keep in mind. The other one that I want to do with you guys before I get in and just show the rest of these is I want to go ahead and do the derivative of the inverse hyperbolic sine function, which again, I've written by definition. It's the natural log of the square root of x squared plus 1 plus x. So again, kind of the idea here is I'm going to go ahead and just kind of write this down here. So we've got d dx of ln of the square root of x squared plus 1 plus x. So really important stuff here is, number one, you're going to imply the chain rule. So the natural log means I have to do 1 over the square root of x squared plus 1 plus x. But then I still have to multiply by the derivative of the rest of that stuff, the square root of x squared plus 1 plus x. So important thing to think about when I take that derivative is I'm going to keep that square root of x squared plus 1 plus x in the bottom, and I'm going to multiply, again, the rest of that stuff. So the derivative of x is just 1, but I got to be careful with that other stuff. So I've still got to take the derivative of that square root of x squared plus 1. So I'm going to do 1 over the square root of x squared plus 1. Oh no, we've got to do the derivative. Actually, it's 2. 1 over 2 times the square root of x squared plus 1 times the derivative of that, which is 2x. So I had to do like 3 layers of chain rule here, which is kind of crazy. Let me just go ahead and mention that this 2 and this 2 are going to cancel out while I'm thinking about it. So right now, let me go ahead and rewrite this. So we've got 1 over the square root of x squared plus 1 plus x times 1 over the square root of x squared plus 1 times x plus 1. So notice it's gotten a little on the messy side here, but we can go ahead and start trying to work stuff out. For example, I can go ahead and I'll write it over here. I can go ahead and make that one big fraction. So we'll have 1 over the square root of x squared plus 1 plus x times, let's go ahead and move that x on top, times the square root of x squared plus 1, and then plus the square root of x squared plus 1 over the square root of x squared plus 1. Notice all I did was make a common denominator with this 1 and this x squared plus 1. Hopefully you recognize at this moment that that numerator has turned into the same as my denominator. So we have the square root of x squared plus 1 plus x times x plus the square root of x squared plus 1 divided by the square root of x squared plus 1. So these denominator or these common factors will cancel, and we're going to be left with 1 over the square root of x squared plus 1. Now, this is very similar. This is looking a lot like what the original function was. If this was just trig, the inverse of sine is very similar to this, but it's slightly different. Again, we're looking for some small sign changes. Um, but so there is my final answer for that. So let me go ahead and scroll on down and show you the rest of these. So again, notice what I'm watching out for, and I wrote it over here in pink, is that the sign changes when we have a reciprocal. So if you're doing secant, cosecant, or cotangent, that's when we're going to have a sign change. But other than that, it's going to follow the same formulas. Again, notice though with hyperbolic cosine, it's just regular sine. It's not negative like it was with trig functions. Other than that, I wrote all of these other inverse hyperbolic functions over here. Notice a lot of these are very similar to what the uh, original function was, what the trig function was, with the exception of some sign changes. There is one other one that I want to point out, which is kind of neat and interesting, is that hyperbolic tangents inverse and hyperbolic cotangents inverse are actually the same derivative, so they actually have the same slope. Which is kind of interesting. Other than that, everything else, again, just keep an eye on this stuff. If you want me to prove anything, if you have any questions, please feel free to ask me at any point. Hopefully this, gets you through the rest of the notes and prepares you for the quiz. If you have any questions, let me know. Bye.